This video gives an example exam question on margins analysis and lead lag compensation. So the purpose of this video is to provide students with an example they can use to test their own understanding. The idea is that you pause the video and try the question by yourself and only look at the solution once you've made a proper attempt. We're going to assume students are familiar with all the previous videos in this series and that we're going to use a standard feedback loop. Now, before you start, make sure you're familiar with mechanistic rules for lead and lag compensation and the attributes of lead and lag compensators, and therefore what each of these can offer. The focus here is on paper and pen solutions, as would be required in an exam where maybe you do not have access to a computer. However, it's worthwhile checking your working with MATLAB, certainly while you're learning, to make sure you haven't made silly mistakes and to help increase your overall skills. Here's the question then. Using hand-drawn Bode, Nyquist and root-loci plots, analyse the closed-loop behaviour of a system G of S with unity negative feedback, and you'll see G of S is given here. Once you've done that, discuss the relative merits of the alternative compensator strategies. You'll see you've got K1, K2 and K3. Now is the time to pause and try this by yourself, and only then come and look at the sketch solution that I will provide. Right, the first thing then we're going to do is look at the Bode sketches. So what I'm going to do is break the frequency range up dependent on the corner frequencies in the system. So I've got omega less than 0.5, 0.5 less than omega less than 2, 2 less than omega less than 5, and omega greater than 5. Now, if I'm looking at Bode asymptotes, in the gain plot I'm interested in the slope, and in the phase plot I'm interested in the phase asymptote. Now, because 0.5 and 2 are both poles, the slope's going to start at minus 20 with the integrator, then go to minus 40, then minus 60, and then back to minus 40. And the units of all these slopes are decibels per decade. The phase asymptote will match, so you'll get minus 90 there, minus 180 there, minus 270 there, and minus 180 there. So that's the basic asymptote information. Now you'll remember I need to put some slightly more precise information to hang these plots. So if I look at the gain, I can take the first corner frequency and find the value of the asymptote at that corner frequency. So the way I do that is just substitute in the 0.5, so I'm going to get 0.4 times 5 over 0.5 times 0.5 times 2, and this is going to give me 4 or 12 decibels. So do remember, this is an asymptote calculation. It's not the exact value of the modulus of G, which will be somewhat smaller. What about the phase? I can also find the phase at some key frequencies. So 2 seems to be in the middle, so we could try 2 and see what we get. So we're going to get minus 90 minus 10 to the minus 1 of 2 over 0.5 minus 10 to the minus 1 of 2 over 2 plus 10 to the minus 1 of 2 over 5. And if you do that, you'll find you get minus 189. So we've gone all the way into quadrant 2. And we might be saying, well, that frequency is clearly too high, so let's try a smaller frequency. So if I go to the other corner frequency, 0.5, and see what I get, minus 90, minus 10 to the minus 1 of 1, minus 10 to the minus 1 of 0.5 over 2, plus 10 to the minus 1 of 0.5 over 5, and that gives me minus 143, which is nicely placed in the region where I really want to be accurate. So I seem to have enough values there to give myself a reasonable Bode diagram sketch. Remember, we're only doing a sketch. If we really wanted an exact plot, we wouldn't be asking this in an exam paper where you did not have access to MATLAB or something similar. So now let's do the sketches. So here's our graph paper. So first of all, I'm going to start with the gain plot. So you remember the first corner frequency was at 0.5. So let's just mark that. That frequency there is 0.5. The next frequency was 2. That's there. And the next frequency was 5. So I'm just marking the corner frequencies so I know where they are. Now, we said at 0.5 we had approximately 12 decibels. So that's what that point there is. And we said to the left the slope was about 20 decibels per decade. So that's like that. Then to the right we said we went down at 40 decibels per decade. So, and we did that until we got to a frequency of 2. So if I follow that down, 40 decibels per decade, and then we went down at about 60 decibels per decade till about 5, and that's getting quite difficult to mark, and then back to 40 decibels per decade. So roughly speaking, that's what my Bode diagram is going to look like. Now, in terms of the phase plot, we started at minus 270, then we went up to minus 180. Oh, sorry, I'm in the wrong question entirely. We started at minus 90. We started at minus 90, then we went down to minus 180, and then we went down to minus 270, and then back to minus 180. So there's your phase asymptotes, and we had 2 specific values which we calculated. We said at a frequency of 2 we had minus 189 degrees, so that point's about there, and a frequency of 0.5 we had minus 143 degrees, so that's about there. So with those values we can see that the plot is going to do something a bit like this. Okay, don't worry about the fact that it's not really accurate, because remember, we're doing a sketch. If we wanted a really accurate plot, we wouldn't be doing it by hand. Okay, next we're going to look at the Nyquist plot. So before we do that, we need to remind ourselves of key quadrants so we don't get confused. So we look down here and we see this corresponds to quadrant 2, and this one here corresponds to quadrant 3. So the plot starts in quadrant 3 and then moves into quadrant 2 and finishes along the negative real axis. So let's sketch that. Oh, we need the intercept as well, just to make sure that we're not far out. So if we look at the minus 180 degree, the intercept is somewhere around here. So I run that up. You can see the gain is of the order of 10 decibels, which is about a third. So the intercept with the negative real axis will be somewhere around minus a third. Now remember, that's only approximate because we're using sketches. So what have we got? We've got the intercept is somewhere around here. We started at minus 90. We came in, we went past minus 180 and then came back. And so we've got a sketch that does something like this. If we add in our right hand turns, then we're going to end up with an overall Nyquist sketch something like this. And of course minus 1 is here. So if I now do my Nyquist stability criteria, I've got NQ equals NC minus NO, and remember, in an exam make sure you write down the definitions of these terms. NQ for clockwise encirclements, NC for closed loop right half plane poles, NO for open loop right half plane poles. Now we've got that NO equals O, and therefore we want NQ equals O, 0. We want no encirclements for closed loop stability. And what you'll see is if K is small, NQ equals 0. You will also see that if K is large, then NQ will be 2. Okay, and that would imply 2 right half plane poles. So that's what you can see from Nyquist. If I do a larger K, just so you can see, with this black plot, a larger K would get something like this, and therefore you can see you get your 2 encirclements of the minus 1 point. What about the root-loci then? So again, what have we got to do here? It's perhaps useful just to remind ourselves of what the system was. So we had S plus 5 over S S plus 0.5, S plus 2, and there was also a constant in there which was 0.4. Not that that really affects the root loci, but we'll put it in. So we had a pole here, a pole here, and a pole here, and we had a 0 at -5. So what you can see is we've got two asymptotes, because there's 3 poles and 2 zeros. The centroid is given by the sum of poles minus the sum of zeros over 2, which is going to be minus 0.5 minus 2 plus 5 over 2, which gives us 1.25. So the centroid is over here in the right half plane. If I mark the bits on the real axis, you'll see odd number to the right means in there and in there, so that pole is going to the left of the 0. These two will join together and go off to the asymptote. So what do you notice? You notice that for large gain you will have 2 right half plane poles, whereas for small gain you will be stable. So let's look at the analysis then, and although we've done some of this, it's important to restate it in a neat form. So we're stable if we have small k. That's what we got from Nyquist. And we're unstable if we have large k. If we look at the root loci, we also found we're stable for small k and unstable for large k. Now that's encouraging because it means we've got the same insight from both of these, but we also discovered if you had large k you had 2 right half plane poles, and if you looked at Nyquist we discovered the same thing. For large k you had 2 right half plane poles. So again, those two are telling us the same thing. I need small k to stabilize large k, and I'm unstable. What about the margins then? Well, let's go back to the Bode diagram and see what it tells us. In order to calculate the margins, I need the crossover frequencies. Now we've already marked one crossover frequency here, the gain crossover frequency, and you can see the gain margin is approximately 10 decibels. Now obviously that's based on a crude sketch. You could do it far more accurately if you really wanted to. What about the phase margin? Well, we need the gain crossover frequency, which is somewhere around here. So we run that down. Make sure that you mark this clearly so people can see what you're doing. And therefore the phase margin is calculated in there, and you can see the phase margin is of the order of 20 degrees. Okay? Remember, that is only approximate based upon the sketch that we've done here. So let's go back. So in terms of margins, we've said the gain margin is approximately 10 decibels. The phase margin is approximately 20 degrees. So in particular, this is too small, so you expect poor behavior. Okay? But because the phase margin is positive, poor, and we can put here but stable behavior. So that's our basic analysis of what we've done so far. Now, next we're asked to look at the impact of different compensators. What happens if we use k equals 0.5? So k equals 0.5 is equivalent to -6 decibels. And therefore, if we want the new gain crossover, okay, we have to do the intercept of the original with +6 decibels. So let's do that and see what we get. So we go here and we're looking for the intercept with +6 decibels. So I'm not particularly precise, but it's, oh dear, I've drifted a bit. Anyway, it's along those lines. So if this is +6 decibels, you can see it's moved us across. We've now got a crossover frequency of around 0.5. and therefore this is the new phase margin, which is going to be of the order, if I get that right, something like 35 degrees. So we've improved the phase margin, okay, from what it was. There would also be a corresponding improvement in the gain margin by this 6 decibels, but I'm not going to worry too much about that. So, what we find is the new phase margin is approximately 35 degrees, which is better. Okay? But still too small. Alright, so the key thing here is demonstrate how you got the new margins. That's key. But also give some comment. And the comment here is that while you've improved the margins, they're still not big enough. Okay? And you perhaps could add, we expect a phase margin of approximately 60 degrees for good performance. It's always worth stating something like this so the examiner knows what scale you're using for good and bad. What about this next compensator? K2 equals 2, S plus 0.05 over S plus 0.2. Now clearly this is a lead. Alright? And the geometric mean of the pole and 0 is 0.1. Okay? So this is where you get the phase rotation. So what we've got to do is go and look at our Bode diagrams and ask us, is this a good place to give ourselves phase lift? So here's our Bode diagram. So where is 0.1? Well, 0.1 is all the way over here. Now, if we give ourselves phase lift here, you'll see that the phase is already at about minus 110 degrees. So if that was to be the crossover frequency, we've already got a margin of about 70 degrees without any phase lift at all. So lifting the phase further still seems somewhat pointless. Okay? At this point, perhaps you want to increase the gain or do something else, but it does seem a bit odd because you're lifting the phase where you really don't need to be. So the sorts of things that you're going to write here is no phase lift needed. Okay? As argument of G of J 0.1 is approximately minus 110 degrees. And therefore, this is a poor design. Okay? Because you're not using the attributes of a lead compensator correctly. Okay? What about this one here? Now this is also a lead, but in this case, the geometric mean is at omega equals 0.1. The beta is 4, which is going to give you a phase lift of approximately 35 degrees. Nobody's going to check whether you've got it exactly correct. Alright, so let's go and have a look and see if that makes sense. Okay, so at omega equals 1, that's down here, okay, we're going to be lifting this by about 35 degrees. So in other words, we're going to lift it up to somewhere like here. Okay? And that will give us a possible phase margin of, now if it's lifted up to about minus 130, of around 50 degrees. Now I'm being very approximate here because remember we're only using sketches. So you could get a possible phase margin of about 50 degrees as long as you can make sure that at the same frequency you need to make sure here that the modulus of GK is approximately 1. Alright? So if this phase lead is at the gain crossover frequency, then you could get a phase margin of about 50 degrees. Now you'll notice that the gain plot already is very close to 0 decibels at this frequency. So what you're really saying is you want the modulus of k to be approximately 1 at this frequency, and you will get a phase margin of about 50 degrees. Now remember, it's an exam, so you can get away with being approximate. Alright, so what we're saying is this is good if the modulus of k is approximately 1 at omega equals 1. Just notice that the typo there, that should say 1. Okay, so what's the modulus of k at omega equals 1? Well, the modulus of k of j1 is going to be 2 into the root of 1.25 over the root of 3. Okay, if I've done that correctly. No, not root of 3, sorry, root of 5. I knew something wasn't quite right. And what you'll find is this indeed does give you 1. Okay, and so therefore, in conclusion, this seems about right. Okay, in terms of what you can do on quick paper and pen exercises, this compensator seems to give you a reasonable phase lead, perhaps not quite enough. You could put may prefer more phase lift, as new phase margin is going to be 40 to 50 degrees, and you might say, really, I'd like it to be 50 to 60 or even 60 to 70, but the examiner shouldn't be testing you on decimal places, they should be testing you on the key insights.